Myself Prayak Patel, working as assistant professor in IT ICT department of LJ Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the new chapter, unit number 6, exploring graph. Now today's topic is introduction of graph. First, consider the outline of the today's video lecture. First is introduction of graph using game. Second, concept of graph. And third, representation of graph. Now first consider how we can use the graph for game playing. Here consider the various problems can be formulated using graph. Game playing application can be represented using graph. You can represent the any game playing thing in using the graph. Now consider one game name which is popular in China. So here consider the some rule for particular game. Here consider the rule one by one. First rule is initially there is a heap of object between two players. Means here consider the two-player game. In two-player game consider the heap of object between two players. Now second step is each player can pick up the object alternatively. Means first select first player, then next select the second player. Like this alternative turn are there. Now third step is each player can pick up at most twice the number of objects than its opponent. Means if the first player pick up the two objects, then opponent means second player pick up the maximum 4 object, not more than that. Or if possible, they may be select the less than of the maximum of 2 times or twice object. So consider this fourth point. An object is removed from the one row at a time. So consider the, for example, 2 rows are there, then initially you can select the object from any one row, not select the object from the 2 rows. Next point, the person who pick up lastly will lose the game and opponent will win. So here consider the last selected object player consider as a loss the game and opponent will win the game. Now consider the one example, and using this example we understand how game playing application is done. For example, heap of object is arranged in 2 rows, namely A and B, and there are 2 players I and U. So here consider the 2 heap of object A and B. In first heap A 3 objects are there, in second heap B 2 objects are there. Now here 2 players are there, first player is I and second player is U. So consider the one by one possibilities for this. Here consider the first possibility, I select the object or you select the object. Here consider the initial step of object A and B as a 3, 2. So we can say that here third column consider as a moves. Means for example consider the first player is I. Then I take one object from B. Here 2 heap of object, first heap is A and second heap is B. So here consider the first I player take one object from B. Then now consider the next step. In next step consider remaining object as a 3, 1. Because already initially 3, 2 object are there. But if you select the one object from B, then remaining object as a 3, 1. Now next turn is here consider the alternative turn. So here consider the next turn for the next player means player U. And you take the 2 from A. Here maximum object selected by the opponent means maximum object selected by the object from the object number A or from the object number B, and you player select the maximum 2 object because opponent select the 1 object. So here consider the 2 objects selected from A, then remaining object consider as a 1, 1. Now turn is for player I. So I take 1 from A. So remaining object consider as a 0, 1. 0 in A and 1 in B. Now turn for the second player U. You take 1 from B. So here consider the last object or last pick object consider as a object 1. One object selected from the heap of object B. So here consider you player select the one object. Here consider I win and you lost, because lastly selected object by you player. So you lost the game and I win the game. Now consider the second option or second possibility. Here consider the more than one possibilities are there. Now consider the second possibility. Initially there are 2 objects. First I take one from A, then remaining object is a 2. Now you take one from B, then remaining object is a 1. Now consider I take one from A, so remaining object equal to 1. Now you take one from B, so remaining object equal to 10. Now last one object are there in heap A, so I take one from heap A. So lastly I select the object, that's why we can say that I lost the game and you win the game. Now consider the another option or another way for the same problem. Consider here initially 2 objects are given. Now I take one from A, then remaining object equal to 2. You take one from B, so remaining object equal to 1. I take 2 from A, then remaining object equal to 1. Then you take one from B. So last result consider as a I win and you lost the game. Now consider the fourth possibility or fourth way. Initially 2 objects are there. I take 2 objects from the B. So remaining object consider as a 0. Now you take 2 objects from A. Then consider one object is remaining in heap A. So here consider remaining object as a 10. I take one from A because there are only one object. So last result is I lost the game and you win the game. And consider the fifth possibility for the same game. Here consider 2 as an initial position. Now I take 2 from the B, means remaining object consider as a 0. Now consider the next 0 as a remaining object. Then you take 3 from A. Then lastly you pick the object. So we can say that I win the game and you lost the game. So here consider 5 different possibilities are there. Now for this possibility or for this game, you can represent the result of game using the graph. So here consider the graph concept for this game. So initially here consider the first possibility as an object A and heap of A and B, and sequence of the operation we already discussed. So here consider the initial position as a 3-2. Okay, so here root node consider as a 3-2. Now from the root node consider the next node. Here consider the after 3-2 next step is 3-1 in this table. So here consider 3-1 as a next step. So here consider the one arrow from 3-2 to 3-1 and consider the 3-1 as a next node. Now consider the next node as a 1-1 in table. So here consider in a graph 1-1 consider as a next node. Now consider the next node as a 0-1. So here consider last node consider as a 0-1. So according to your first solution or first possibility, your graph like this. Now consider the second possibility. In second possibility initially there are 3-2, then 2-2, then 2-1, then 1-1, then 1-0 according to our second table. So here consider initially node as a 3-2. We already write the one node as a 3-2, so use this node, not repeatedly you write the second time 3-2 node, because this is considered as a graph. So here consider 3-2 node as an initial node. Now consider the next node as a 2-2. 2-2 node is not available, so write the new node as a 2-2. And here consider the yellow shaded line for the second option. So here consider 3-2 to 2-2 as your second node. Then consider the next node as a 2-1. In next node 2-1 consider the possibility. After that 2-1 consider the next option as a 1-1. After the 1-1 consider the last option as a 1-0. So here consider the last node as a 1-0. Here consider last node 1-0. Now consider the another option. In another option consider the sequence as a 3-2 as a initial state. After the 3-2 next node is 2-2. So already 2-2 node are available. Now after the 2-2 consider next node as a 2-1. 2-1 node already available. Now next node is 0-1 and 0-1 node already available, but here we consider the 2-1 as a previously node and next node as a 0-1. So here green shaded line consider your path from 2-1 to 0-1. So here consider this is a third option. Now consider the next option and fourth option of your example. Initially we have a 3 2 node, then consider the next node as a 3 0. So here 3 0 node is not available, so consider the new node as a 3 0 node. After the 3 0 node, consider the last node as a 1 0. So here consider this path as a 3 2 to 3 0 and 3 0 to 1 0 for the fourth option. Now consider the next option and fifth possibility is initially 3 2, then consider the 3 0. So here consider already 3 2 node are there and 3 0 node are there and already paths are available. So no need to any change in this graph. So consider this graph as a final graph for the given example of the name game. So here consider introduction of graph using game theory. Now consider the next topic, concept of graph. Now first we understand what is graph. Here consider one graph in this figure. Now consider the definition of graph. A graph is a collection of nodes and edges. So here we can say that node as a vertices, can also consider the edges, means consider as a link. So here in this graph consider the V and E. So here consider graph G equal to V comma E. V means vertices or nodes and E consider as a edges or link. So here in this graph we can see that V equal to nodes, vertices and points. So here consider A, B, C, D, E, F consider as a nodes or vertices. And here we see that edges are there. So E consider as a edges or link. So here consider A to D link are available, D to E link are available, F to E link are available. So this all consider as a edges. So this is a simple consider as a graph. Now next definition is directed and undirected graph. Now first understand what is directed graph, then consider the undirected graph. Directed graph means a graph is in which every edge is directed from one node to another node is called the directed graph. So here consider the first figure as a directed graph. From the any node to any other node, consider the edge which are directed. Some direction are there from one node to another node. So this is called the directed graph. Now second definition is undirected graph. A graph in which every edge is undirected and no direction is associated with them is called the undirected graph. So here consider the second figure as a undirected graph. In undirected graph, edges are available but no any direction from 1 to 2 or 2 to 1. So here consider this graph as a undirected graph. Now consider the next concept of graph as a multigraph. Here consider the definition of multigraph. A multigraph is a graph which is permitted to have a multiple edges, that is edges that have the same end node. Means here consider the between the two nodes we have a multiple edges or path are available. So here consider the example of the multigraph. For example, this figure consider as a multigraph because here between these two nodes there are three paths are available. So from node 1 to node 3 you have a three option or three way from move the node number 1 to node number 3 or node number 3 to node number 1. So this is considered as a multigraph. Now consider the another figure for the multigraph. Now in first figure G1, consider the A and B node. Between the A and B node there are two edges. So here consider from move from A to B we have a two path. Here consider B to D path. Here in B to D, between the node B and D there are three edges. So consider these three edges as a multiple path or multiple way available from B to D. So here consider this graph as a multigraph. So in undirected graph, if the two edges between the any two node, then this graph consider as a multigraph. But in second figure consider G2 as a directed graph. In directed graph, not necessary that if two element or two node having the more than two edges or two edges, then this is a multigraph. But because here consider the direction, in which direction A to E or E to A is must remember that. So here consider the second figure. In second figure consider the edge from C to D. In C to D there are 3 edges. So we can say that if more than 2 edges are there, then this is considered as a multi-graph for directed graph. In undirected graph, there are only 2 edges, then we can say that this is a multi-graph. Here consider the B to C edge. In B to C, both the direction are same from B to C, then this is considered as a multi-graph. But in A to E, here consider 2 edges are there, but from A to E, one direction, and second direction from E to A. So this is not considered as a multi-path. Okay, now this is considered as a multi-graph. Now next definition is sparse graph. In sparse graph, definition of sparse graph is a graph in which the number of edges is close to the minimum number of edges. For example, consider the one figure for the sparse graph. Here consider the total 5, 6, 7 number of nodes are available. Then here consider minimum number of edges, means here only 1, only 2, 3 edges are available, but maximum edges, many edges are possible, but here only consider the minimum number of edges. So we can say that sparse graph can be disconnected graph because each and every node are not connected with each other. So here consider this graph as a disconnected graph. So here with compared to number of node, here minimum number of edges are there, then it's called the sparse graph. Now consider the next definition as a dense graph. Dense graph is opposite of the sparse graph. Here consider the dense graph is a graph in which the number of edges is closer to the maximum number of edges. Means we can say that the not totally n number of or n square divided by 2 number of edges, but here only consider the with compared to node there are many number of edges are available. For example, here consider the node number 1 to node 2, node 3, node 4, node 5, node 6 paths are available, but from 1 to 7 paths are not available. But this graph considered as a dense graph because with compared to number of nodes there are many number of edges are available. Now consider the next definition as a complete graph. Now complete graph means an undirected graph in which every vertex has an edge to every other vertex. Means we can say that here 5 nodes are there. So each and every node directly connected with remaining all the nodes. So here consider, for example, this one node connected with 2, 3, 4, 5. Every node connected with every other node. So this is called the complete graph. So difference between complete graph and dense graph. Here consider the dense graph, 1 or 2 edges are less than the complete graph is possible, but complete graph completely have a connected with remaining all the nodes. Now consider the next definition as a weighted graph. Here consider the weighted graph means each and every node edges have a some weight. For example, here consider this graph as a weighted graph. Weighted graph is a graph for which each edge has an associated weight. Means here consider from 1 to 2, 1 edge are there, and here consider the weight for this edge as a 1.2. Here consider the 1 to 4 edge. Here weight consider as a 0.5, like this. So here for each and every edge some weight are given. So this is called the weighted graph. In second example, consider 1 to 2 as a 2 as a weight. In second, consider 2 to 5 as a 5 weight, like this. Now consider the next definition as a connected graph. Here undirected graph is called the connected graph if every vertex is reachable from the all other vertices. So here consider the, for example, 1, 2, 3, 4, 5, 6 nodes are there. Each and every node are connected with each other. Means here we can say that path from node 1 to any node are available using the any number of intermediate node. If you want to find the path from node 1 to node 3, then path is available like 1 to 5, 5 to 6 and 6 to 3. So here each and every node are connected, not disconnected. So this graph considered as a connected graph. Here second graph considered as a disconnected because here if you want to move from node 1 to node 6, then no any path are available. If you want to move from node 1 to node 3, then no path is available. If you move from the node number 1 to node number 4, then path is not available. So this is called the connected and disconnected graph. Now consider the next definition as a subgraph. Vertex and edges set are subset of given graph G is called the subgraph. For example, given graph G consider as a G equal to VE. Then subgraph consider as a G dash equal to V dash E dash. Then consider the V dash is a subset of V and E dash is a subset of E is called the subgraph. Here consider the one figure. This figure consider as a graph. Here total 6 number of node are there. Now consider the subgraph of the graph G as a node. Only 3 node are there. Node number 1, node number 2 and node number 5. But here remember that 3 node is same as it is and 3 edges is same as it is, then is called the subgraph. A supergraph of graph G is a graph that contains the G as a subgraph. Now consider the tree. What is the definition of tree? Here consider the tree means in these two figures, first is considered as a graph but second one considered as a tree. An undirected graph is a tree if it is connected and does not contain a cycle is called the tree. So here consider in first figure there are one cycle between node C, D and E is called the graph, not considered as a tree, but second figure considered as a tree because there are no any cycle between any nodes. So this is considered as a tree. Now next topic is representation of graph. Two ways of representing a graph. First one is adjacent matrix and second one is adjacent list. So here consider the one by one option. First consider the representation of graph using adjacent matrix method. For example, here consider the one figure and using this figure you can represent your graph. Here consider the G equal to VE be a graph with n vertices. The adjacent matrix of G is a two-dimensional n by n array. Here consider the total number of nodes in this graph consider as a 0, 1, 2, 3 means total 4 number of nodes are there. But if we want to represent this graph for the 4 node, then consider the 4 cross 4 matrix, n cross n matrix. Now consider the value of the matrix as a if the edge between Vi to Vj means edge available from Vi to Vj, node 0 to node 1 or node 0 to node 2 like this is in Eg, then adjacent matrix Ij equal to 1 means path from any node to any other node are available. Then consider the location. For example, path available from 1 to 2, then location 1 to consider as a 1 and remaining all node consider as a 0. If there is no such edge in Eg, adjacent matrix Ij equal to 0 means path not available from any node to remaining node, then consider as a value 0. So here consider from the 0 for first row consider for the node number 0, second row consider for the node number 1, then node number 2, then node number 3. According to row consider the column. Initially consider the column 0, then 1, then 2 and 3. Here from the node 0 to 1, 2, 3 path available, then we can say that initially we put the 0 because 0 to 0 path is not available. Then 0 to 1, 2 and 3 path is available. So here write the 1, 1, 1. In second row consider the 1 to 1 path is not available but 1 to 0, 1 to 2 and 1 to 3 path is available. So write the 1, 0, 1, 1 like this. Using this method you can represent your graph using matrix. Now consider the second example. Here consider the weighted graph. In previous case we simply represent the graph for the only unweighted graph. Here consider the weighted graph. Consider the total number of nodes are A, B, C, D, E means 5 number of nodes. So represent this graph using 5 cross 5 matrix. First consider the row as a B, C, D, E and column consider as a B, C, D, E. Now A to A path is available? No. So write the 0. Now consider A to B. Second block consider as a to B. In A to B here path is available? Yes. Then consider the 7 because here weight of the path A to B or edge from A to B weight equal to 7. So here in this table write the weight, not write only 1. In previous case we write only 1 because there are no any weight are given. That's why we can write the 1 for the available edges and 0 for the not available edges. But here consider the 0 for the not available edges and weight of the particular edge for the available edges. So here consider 1 A to B as a 7, A to C as a 8, A to D as a 5, A to E path is not available, so write the 0. According to same way we can write for second row, means for the B to A path available, yes, then distance 7. B to B path is not available, then 0. B to C path not available, then 0. B to D path available, then distance equal to 10, and B to E path available, distance equal to 6. Like this you can represent your matrix using the using matrix you can represent your graph. Now consider the next step as a adjacent list, means matrix or graph can be represented using adjacent matrix and adjacent list. So second method consider as a adjacent list method. In adjacent list method, adjacent list representation is one of the alternative to adjacent matrix. For every vertex, adjacent list store a list of vertices which are adjacent to current node. Means here consider the one example. For the any node, you can represent the one linked list form. Means you can consider as a number of node are there. Here consider 0 to 6 node are available. So first column consider from 0 to 6. In 0 to 6 column, initially for the 0 row, consider the which node are connected with the node number 0. So here consider the in this figure 0 node connected with 1, so write the 1, then second connected with 2, then connected with 6, then connected with 5. Means in 0 row consider the column as a 6, 5, 1, 2. Means you can connect the node number 0 with the node number 6, node number 5, node number 1 and node number 2. Here sequence is not matter, you can write the 1, 2, 5, 6 or 6, 5, 1, 2 or 6, 5, 2, 1 like this. Because only we represent this adjacent list for the graph. We can say that using the graph you can represent the list, and from the list you can also draw the graph. These two things are done. Here consider the second row as a 1, means node number 1 connected with which node? Only node number 0, so we can write only 0 in second row. Then consider next as a 2, in 2 row consider the which node connected with node number 2, so here consider the 0. For the third, 3 node connected with the 4 and 5, fourth node connected with the 6, 5 and 3, fifth node connected with the 3, 0 and 4, and sixth node connected with 0 and 4. So you can represent your graph using adjacent matrix as well as adjacent list. Now in today's video lecture I discuss about the basic concept of graph, some definition of graph, then how we can represent the graph using adjacent matrix and adjacent list. Now in next video lecture we continue this chapter. Thank you for watching this video.